Okay, so the final question is a little bit more conceptual, but I think it's still a good question. So in this one, a T-shaped tube with a constriction is inserted in a vessel containing a liquid as shown above. What happens if air is blown through the tube from the left as shown by the arrow in the diagram? Pause it, try it on your own, and then I'll kind of go over it in a second. But yeah, try it, have an answer, and then we'll go over it. Okay, so I think this is a really good question because it really deals with a lot of conceptual ideas. So with this one, we are at first, let's think about before we even have this air flown in there. Our fluid is presumably at atmospheric pressure. It doesn't say we're in like a vacuum tube or anything. So we are at atmospheric pressure. We have this outside air that is pushing down on our fluid. Does it say what fluid it is? Liquid, whatever. So it's pushing down on this liquid, and we have this open to the air. And if we're at the same height, that means that we have the same pressure associated with it. So we talked before with this this P equals P naught plus rho GH. If it's at the same height, it's got the same pressure associated with it. So everything here, this is open to the air. This right here then means that in this column we are at atmospheric pressure. So then what happens is we have this air go through here, and we don't have to worry too much that the area gets smaller. I mean, we could say something about A1 V1 equals A2 V2. And then the area over here is big, the area gets smaller, so we go from big area, small velocity, to small area, bigger velocity. But pretty much right here, we have some pretty fast moving air. It's pretty speedy. Fast. And we said in, I think, question 2, if our air is moving quickly, that means that there is a lower pressure associated with that. So we could do out really quick, just to write out Bernoulli's equation, this P1 plus rho G Y1 plus 1/2 rho V1 squared equals P2 plus rho G Y2 plus 1/2 rho V2 squared. The height term is just going to cancel out. 1/2 rho V1 squared equals P2 plus 1/2 rho V2 squared. Alright, so we see here that we can call this position 1 and call this above the pipe position 2. At position 2, we said we're moving fast, so we have a fairly big kinetic energy term, which means that our pressure is going to be small. And on the other side, it doesn't really matter, but we have a smaller associated kinetic energy term, which means we have a higher pressure, but it doesn't really super matter. What matters is this idea that by blowing this air through here, by doing this fast air, at this position above the liquid, we are at a low pressure. So we are at a pressure that is lower than atmospheric pressure. So we have this atmospheric pressure pushing down out here, and we have this push. Before we had atmospheric pressure in here, it was equal, everything was in this nice equilibrium state, but now we kind of have this lower pressure. We have less particles that are pushing down on it, so this liquid has the ability to rise up. So because it doesn't have that atmospheric pressure on it pushing down, it has a less than atmospheric pressure in here. We have a push here from the atmosphere. No longer have atmospheric pressure pushing back on it, it raises up. So we can be at this nice equilibrium state where our fluid is not moving anymore. But because we have a lower pressure up here, this fluid is allowed to rise until it finds that new equilibrium height.